Chapter 3-3. Increased Training Datasets, Part 2. In Chapter 3-2, I compared Model A, trained with a subset, and Model B, trained with the entire dataset. Now, in Chapter 3-3, I compare Model A, trained with a single dataset, and Model B, trained with double datasets. This study aims to confirm Chapter 3-2 findings, as training samples increase from thousands to tens of thousands. 1. More training samples widen confidence assessment range, potentially boosting samples exceeding 95% confidence. 2. Yet, higher sample quantity doesn't always improve accuracy for samples above 95% confidence. As shown in this figure, Model A is trained with a single dataset to learn 8 high-level labels using a neural network, while Model B utilizes double datasets. Trained models A and B are evaluated based on 2 criteria, as depicted in this figure. 1. Determine which model collects a larger number of samples that exceed the 95% confidence threshold. 2. Evaluate which model achieves higher accuracy for the selectively collected samples. Chapter 3-3. Test Conditions. In this assessment, I utilize models A and B. Model A, trained with one of 3 datasets, emphasizing grandparent-level labels. Model B, trained with 2 of 3 datasets. Since models A and B are tested on the same dataset, as shown in this figure, each with 3 dataset types, there are a total of 6 test results. Chapter 3-3. Best Test Case. In this evaluation, it's unclear which model, A or B, performs better based on the following findings. Step 1. The difference in training samples between Model A and B averages around 18,000 samples, compared to about 6,700 in Chapter 3-2. Step 2. The gap in selected testing samples surpassing the 95% confidence between Model A and B averages around 5 samples, compared to about 10 in Chapter 3-2. Step 3. There's no significant gap in prediction accuracy for the selected samples between Model A and B. Sub-conclusion: despite the larger difference in training samples between Model A and B compared to the previous scenario, the performance gap has decreased. Conclusion: therefore, it remains inconclusive whether Model B outperforms Model A. Chapter 3-3. Sample Quantity and Confidence Range Relationship. When the metacognition AI learns more training samples, its confidence assessment range widens for the same testing sample. This widening range results in an increased number of testing samples surpassing the 95% confidence level. For a clearer understanding, I verify an example from testing datasets 1 and 2. Testing dataset 1. Model B had 16,830 more training samples compared to Model A, as seen in this figure. This resulted in a widened confidence range for the same testing samples. Consequently, in this figure, Model B had 15 more samples exceeding the 95% confidence threshold. Testing dataset 2. Testing dataset 2 is similar to testing dataset 1, but with a slight difference. In this figure, Model B showed a wider confidence range than Model A. Consequently, in this figure, Model B had 4 more samples surpassing the 95% confidence. This difference is relatively smaller compared to the 15 sample gap observed previously. Chapter 3-3. Testing Dataset 1 Test Results. In summary, Model B, trained with double datasets, outperforms Model A, trained with a single dataset. As shown in this figure, Model B gathers a higher proportion of samples, 88.2%, compared to Model A, 79.4%. However, Model B's prediction accuracy for the selected samples is 91.9%, slightly lower than Model A's average accuracy of 92.4%. Chapter 3-3. Testing Dataset 2 Test Results. In summary, Model B, trained on dual datasets, outperforms Model A, trained on a single dataset. As depicted in this figure, Model B collects a slightly higher percentage of samples, 82%, compared to Model A, 79.6%. Moreover, Model B achieves a prediction accuracy of 89% for the selected samples, slightly surpassing Model A's accuracy of 88.9%. Thank you.